Okay, so welcome back everyone. This is MP Live Lessons, and now that the lessons are free, we're going through Physics Paper 1, and you may be asking me that if you're doing any of the tiers, any of the triples or combines, and so on, but I'm doing everything. Based on the advanced information in the bottom right, you will see the relevant information that's, well, going to be in your exam. So firstly, we're going to start with topic 1, energy and systems. So first, you need to know what's meant by a system. So a system is a group of objects that interact. And usually if it's a closed system, nothing can get out, nothing can get in. So that's the same for mass or energy. For topic 1, you'll need to know about the types of energy stores or transfers in systems. For example, you'll need to know what's meant by kinetic energy. This is movement. You'll need to know about elastic potential energy. So this is like when you bend things. Next, you'll need to know about thermal energy, which is simply heat, as well as gravitational potential energy, so you gain it by lifting things up into the air. Lastly, chemical and electrical um, potential energy, which should make sense on its own. Chemical, that would be like batteries, for example, and electrical is just electricity. Next, you'll need to know about transfers of energy. So you need to describe energy transfers in a system. So from one to another. And remember, you need to mention if the store increases or decreases. We'll just test the microphone right. Um, for example, an electric kettle of water. So simply put, you've got the electricity coming in, so that's the input. And this transfers to the thermal energy of water because it heats up. Another example could be a petrol car that's moving or that has its engine running. So its input energy would be chemical because that's stored in the fuel or the bonds. Now, a good thing to note is that this will decrease as the car runs, and this gets transferred to its output energy, which is mainly kinetic, which is for moving, but you get wasted energy or energy that you don't want to be transferred to. For example, some of that chemical energy will end up being transferred to the surroundings as thermal energy. That's the heat or how hot the car gets. You may also get some sounds as well. Another example could be a football being pinged, or rather kicked upwards, before it's about to fall back again. So when it's kicked for a start, you've got chemical energy from your body, and this gets transferred to, or this chemical energy store decreases, and then the kinetic energy of the ball increases, so it gets moved by your leg. As well as that, when the kinetic energy of the ball increases, so when the ball starts to move, it goes upwards. And when it goes upwards, it will gain gravitational potential energy. So in other words, it will gain energy from gravity, and then that can get released again when it falls back down. So when it goes up, the higher the ball goes, the more gravitational potential energy it will get. Then when it goes back down, the opposite will happen. So as it loses its gravitational potential energy, that again gets transferred to its kinetic energy store. So in other words, as it goes down, it goes faster and faster until it hits the ground. The last example I'll give is a high jump athlete falling into a crash mat. So a high jump athlete will fall from a high place, so that will be, again, gravitational potential energy decreasing as he falls down, and that will get transferred into kinetic energy. He'll move faster and faster, and then when he lands on the crash mat, that crash mat will absorb his kinetic energy and stop him from moving gradually, and it'll start to compress a bit so that it gains elastic potential energy because it gets compressed. So when falling, so the gravitational potential energy will decrease, and as a result, the kinetic energy will increase. When you're landing, the kinetic energy will decrease, so you'll slow down. And the elastic potential energy is used onto the crash mat or the soft foam. So this could be something that's like a 2 or 3 mark question. And just remember, overall, that you need to state the initial um, energy potential store. So that could be, let's say, kinetic, that's moving, and then what it gets transferred to. So what happens, and then it gets transferred to, let's say, another one. Let's say, again, in the previous example, the elastic potential energy. And you'll need to mention that the first one decreases, and that energy that gets transferred to the other store. So you can think about it like a beaker. So this contains, let's say, some energy. Eventually, that could get transferred, but overall, total energy stays the same. Next, you'll need to know how to calculate some quantities of energy themselves. So we already know what type of energy store is associated with each. For example, kinetic was movement. So we know what factors will change it. So you'll be given a formula sheet, but the units aren't in the equations. And you'll usually use standard international ones, or SI units, if your physics teacher says it in that way. So for example, for distances, it will be in meters. Energy is always measured in joules, unless you're talking about large quantities. And then mass is, for example, is measured in kilograms. And sometimes, if you're higher tier, you may need to convert. So I'd like to label each formula with the correct units. For example, kinetic energy, this is for movement. So this is equal to half times the mass times the velocity squared. Now mass, its standard unit was kilograms, and the velocity, its standard units are meters per second. Next is gravitational potential energy. So this is where you can probably lift an object further up into the air or simply let it go. So that's equal to the mass times its gravitational field strength. So that's how strong gravity is in somewhere, let's say Earth. And that's also multiplied by the height. So the units for each, the mass would be in kilograms, the gravitational field strength would be in newtons per kilogram, and the height would be in meters. Next is elastic potential energy. So that is going to be 1/2 times the spring constant times the extension squared. So that's where a spring will either get longer or shorter, and that will involve a length. So the units for each would be, the spring constant would be newtons per meter, and the extension would be meters. And lastly is thermal or specific heat capacity. So that's a link to another unit. So that would be its mass times specific heat capacity times the change in temperature. And the units for each would be mass in kilograms. Now, specific heat capacity is a strange one, and that's in joules per kilogram degrees Celsius, written like this, and you'll see why in a later unit. And then the change in temperature is just how you measure temperature, which is degrees Celsius. Now, the ones I'd specifically want to highlight or learn would be specific heat capacity, the spring constant perhaps, but this may not be needed, the gravitational field strength, because these are really funny units, to be fair. So I'd suggest taking a quick screenshot right now before we move on. Next, in terms of energy, we need to talk about cooling and heating. So in terms of energy stores, especially thermal ones, now why do things heat up or cool? So think about, let's say, a bowl of hot soup that cools down in a room. In this case, the soup is warmer than the room. As a result, since things are warmer, these objects will radiate or release more radiation or more thermal energy. And the key word or phrase here would be it releases more thermal energy than it absorbs. Because anything can absorb heat or thermal energy. For example, if you put the soup in, let's say, a microwave or oven, they would be in something even hotter than the soup. So now that would absorb more thermal energy. But in this case, the soup is warmer than the room, and warm objects will release or emit more thermal energy than it absorbs. That would be something he'd want to learn. And then the opposite could be said for cold milk that warms up. So the milk is cooler than the room. This time, colder objects will absorb more thermal energy or radiation. So colder objects will absorb more thermal energy than it emits or releases. So it will gain more thermal energy than it loses. And I'll just highlight the top if it makes any more sense. Next, for combined science, you'll need to know about the required practical for specific heat capacity. So the overall purpose is to find the specific heat capacity of a material. So this is how much energy is needed to heat a kilogram of that substance by 1 degree Celsius. So that's why the units were joules per kilogram degree Celsius. Because you need more energy to heat up more of a substance, or by like more, heat it more in terms of temperature. So increase its temperature a lot more. Now to find this, you would actually heat some sort of object up, let's say a block of metal. And along that, to heat the metal, what you'd use in what I call the best setup is a power supply and wires. So that's going to supply power to a heater. And usually you'd use a stick heater, which gets hot and will heat the object that you want to heat. You'd also want an ammeter, a stopwatch, a container with insulation, because this prevents any heat being lost from that block that you're heating up. Your block of material, obviously, and you need to know its mass. This is important because that's going to be part of your units or how you find the specific heat capacity. And then lastly, a thermometer to measure the temperature of that block that you're heating up. Now, you notice I've placed an asterisk. Now, that's because you need these to figure out like how much energy is transferred to the block in terms of heat. If you remember from chemistry, you could remember that power equals the current times the voltage or potential difference. So that's why usually in this practical you would use an ammeter and a voltmeter in their appropriate places. So let's say if you had your heater, which will draw in a loop, and did your power supply like this, what you'd do is you'd place your ammeter in series and then your voltmeter in parallel. But to make things simpler, what you could do is simply put a joule meter in the circuit. This will just tell you how much energy is transferred to the block or through the heater. Next, for the method itself, which could be a 6-mark question, you'll need to sort of know the soft well. So first, you'll need to measure the mass of the substance or the block that you're heating, and you'd usually want to use a small block or liquid, so it all heats up evenly. I would avoid using a big block that's probably quite wide, like a 30 centimeter ruler cube, because the inside is going to be hotter than the outside and you won't get an accurate temperature. So after you've measured the mass of the substance, you'd use something like a top pan balance. You'd then insulate the material, and you can use, let's say, an insulating material like cotton or paper if it's solid, or you can use a polystyrene cup if it's a liquid. And then you'll connect the heater to a power supply, and then you can have an ammeter in series and the voltmeter parallel to the heater. Or you can just cross this out, connect a voltmeter, or actually a joule meter. So this just instantly tells us how much energy is being transferred. It's cheating, but it works. And what you'd do is you'd measure the initial temperature of the material with a thermometer. Then you'd switch on the power supply. If you're using a joule meter, it doesn't matter because the joule meter, you'll see it will start to increase. And you also um, easily record every so often. But if you're using a voltmeter and an ammeter, you'll need to record the voltage and the current. This gives you your power rating. And then, after every 30 seconds, when you switch the power supply on, you'll record the temperature of the material every 30 seconds. So regularly. Because sometimes it can take a while for the actual heater to heat up, and then that will heat up the block itself. Then what you do is you'd repeat step 5, checking if the current remains constant, if you're using that method, until a total of 12 readings are collected. So that's over 6 minutes. And then you repeat the whole thing again to calculate an average temperature increase. What you'd then do, you'd do a lot of maths. If you're going to calculate the specific capacity from the results only, what you'll have possibly the time in a column or just energy. So if you've used the ammeter and voltmeter, or it says in the question, you'll first, to find the power of the heater, is to multiply the voltage and the current. And then what you'll do is to find the energy transferred as you multiply this power rating by how long the heater was turned on. So this tells us the energy transferred or to the like block that you heated up. What you'll then usually is plot a graph of the results, and you'll have the x-axis labeled temperature and the y-axis labeled with energy transferred. So you get something like this. So at the start, you may get a curve before it then starts to just go in a straight line like this. So as more energy is transferred to the block you're heating, the temperature will increase at a constant rate. And remember that energy can be obtained by the power rating, which is from the voltmeter and ammeter, or just simply use a joule meter, which will just tell you how much energy has been transferred, let's say every 30 seconds. Next, you'll need to know how to calculate the specific heat capacity from the results. So what do we know about specific heat capacity? So we know its formula with it. So you've got the change in energy is equal to the mass times the specific heat capacity times the change in temperature. So if you remember with the graph, you had temperature on the x-axis and then energy on the y-axis. Now, what you could calculate perhaps is the gradient. So if you remember, the gradient from maths is the change in y divided by the change in x. So that would be the change in y, the change in energy, divided by the change in x, which would be the temperature. Now, using this formula, we can swap this and put this here instead. And what you notice is you have this triangle with this angle or theta sign, so they cancel out. So what you just found out is that the gradient of the line is equal to the mass times the specific heat capacity. What you also know, coincidentally, is the mass of the material. So therefore, to calculate the specific heat capacity, you need to divide the gradient by the mass. So gradient divided by the mass. And just remember that the axis is the right way around, and it's the energy on the vertical axis or the y-axis, and the temperature on the x-axis. Otherwise, this may not work as intended. Next, I think for triple science, they may need to know about power. So before using the formula, we need to know that the work done is the energy transferred, let's say in electricity, or just anything. These have similar meanings, as I've said. Work done would be usually to do with the force, whereas energy transferred would be, let's say, something heating up. Now, power is how much energy is transferred from one star to another per second, so how fast the energy is transferred. So here's a thought. So compare the work done or the energy transferred along with the power of these two systems. So two forklifts with the same mass and same height, they'll lift up some crates. So let's say they'll be 10 kilograms each and they'll lift them up 2 meters. However, they do it in different times. So one does it in 10 seconds, the other in 20 seconds. As you can see that this forklift will have a higher power. It will do more work lifting those crates up in less time. Whereas the other one with 20 seconds has lower power. And for both, so the work done would be the same for both. So essentially they've done the same thing, but at different speeds, perhaps. Now, for triple science, they'll need to know about the conservation of energy. So this would be to do with closed systems. So the definition is that the total amount of energy in a closed system, as in when nothing can escape or enter, That's where the energy in total remains constant before and after energy is transferred. And that means you can't have energy being created from nowhere, and you can't have energy being destroyed and gone to nowhere. For example, this can explain dissipated energy. So we talked about energy transfers earlier. Now, the thing is, not all of the energy that we put in, as in the input, gets to transferred like to what we want. For example, I used a car engine as one of the examples. So ideally, the chemical energy is transferred to kinetic energy. However, some energy is transferred to other stores, such as thermal energy, that's heat. Some gets lost as sound. That would also be kinetic, but that's different. And usually, the thermal energy can be caused by the actual heat itself in the engine, or perhaps really from moving parts or friction. This can include the brakes as well. Another example could be a kettle. Most of the input energy from electrical is then transferred to thermal energy. However, even if it goes to the same energy store, which is thermal, it will heat up anything. Some of it is lost elsewhere. For example, if you've got just a random pot here, which I'll draw a kettle of, some of it gets lost through the container. So energy is lost to the surroundings, or thermal energy can be lost to the surroundings. So this can be like, for example, the container getting hot, and that will transfer energy to the surroundings because remember, hotter objects will emit more of this thermal energy than it absorbs, so it will lose it overall to the surroundings. So we can actually choose certain devices that are more what we call efficient than others. So we can calculate the percentage or proportion of what energy is lost or dissipated from a transfer. If you remember, if something is more efficient, more of its input energy is transferred to the useful output. So for example, something more efficient, like a more efficient car, it will use all of its energy to kinetic energy, perhaps. It won't get lost, let's say, to heat or thermal energy, sound, and so on. The same could be said for power. It'll just replace energy with power. So useful power divided by the input power. One example of some efficiencies could be e-bikes, electric cars, and even some bikes as well. So these will have electric motors and could do something called regenerative braking. Now, this would improve the efficiency of the bike because if we look at energy transfers, if it regenerates, it will recharge the battery. So the kinetic energy, when we want to like get rid of it or decrease it, such as to slow down, This will instead get transferred to electrical energy. So this will be stored in the batteries again until it can be used, let's say, when you want to increase your kinetic energy again. So you brake, it recharges the battery, and then that energy can be used again to make you go faster again. Some other uses could be perhaps to extend your life of the battery. It can make you go faster perhaps, so that can boost you when you accelerate again. Now, here's something to think about. So suggest why regenerative braking is more commonly found in cars, not bicycles, and think about the kinetic energy formula. So kinetic energy is equal to half times the mass times the velocity squared. Now with bikes, they'll have a much lower mass, so there won't be as much kinetic energy, and furthermore, they'll have a lower velocity. So overall, there's not much energy to get back. Now for triple science, they'll need to know about the required practical, which is testing some insulators. So one variation could be testing the type of insulation. So we've got some variables. So the independent variable will be the type of insulation. So this would be a material often. The dependent variable will be how effective it is as insulating, so the temperature decrease. If it's a better insulator, you'll see a lower temperature decrease over time because less energy is lost to the surroundings with better insulators. And as controls, you'd have perhaps the mass of water or the object. You also have the number of layers of the insulation. So we could have to test one layer of, let's say, cotton versus one layer of newspaper. You could also have the starting temperature of the hot object. Now, for the method itself, you'll start with a small beaker and a larger beaker. And what you'd do is you'd boil water and pour 100 cubic centimeters into the smaller beaker using a measuring cylinder. So that's going to be your hot water. What you're going to do is cover the top of the larger beaker using a lid and leave a hole for the thermometer to put in. And then you'll record the starting temperature of the water and start a stopwatch immediately. And basically, you'll record the temperature every 2 minutes for a total of 16 minutes while the water starts to cool down. And then you'll repeat the whole thing, except that you'll use different layers of insulation, ensuring you've got the same mass, the same number of layers, the same thickness as well. And remember, try and use the same volume and starting temperature of the hot water. And you may even, if you have time, to repeat these single tests, so you can try and calculate your mean and eliminate anomalies to make sure that your data is valid. Now, Testing insulators for triple science may have another variation. Instead, you'll test the thickness of the insulation. So the variables will change this time. So this will be the thickness for the independent variable. This could also be the number of layers. Again, you'll still measure the temperature of the water or temperature decrease. And lastly, you'd also control other things such as this time you're going to control the type of insulator. This will be the material, the starting temperature and mass of water, and so on. So this time, the practical is exactly the same, except for the changed orange bits. So you'll repeat the investigation with different number of layers of insulation or different thicknesses. This time you'll have the same mass per layer, you'll have the same material, and you'll have to cover all the sides of the small beaker. Now, for Combined Science Foundation, you'll need to know about energy resources. So first, what do we mean for energy resources by renewable ones, non-renewable ones, finite ones, and sustainable ones? And could you list a few examples of each? So first, renewable ones would be ones that are replaced at the same rate they're used. A good example could be wood. We can plant as many trees as we cut down to produce energy, let's say for electricity. Whereas non-renewable ones, these are ones that can't be replaced at the same rate they are used. One example of these would be fossil fuels. They can't be replaced at the same rate they are used. It would take millions of years once again to form these same fossil fuels. Now, finite ones have like a limited supply. So once they're gone, they're gone. And sustainable ones may have a limited supply, but we can meet our needs with this resource and not compromising the needs of future generations. So usually renewable and sustainable resources are similar, they'd go hand in hand, while non-renewable and finite materials are also similar, they also go hand in hand. Now, you'll need to know more about energy resources, so you can try and weigh up, perhaps, in an evaluation question, the benefits and drawbacks of each energy resource. That could be linking to chemistry or even geography. You'd have to think about not only if it's sustainable or renewable or finite, or non-renewable and so on. For example, by its cost. For example, this is why we are still perhaps using oil. It's still cheap. how much energy it produces, for example, per kilogram of fuel you burn compared to, let's say, a panel of a solar panel. How much energy does that produce, let's say, in a year? Its reliability. So can you produce energy 24/7 or whenever you like? Can you produce more energy when you need it more? For example, in the morning when you're cooking hydroelectric dams or nuclear electrical productions, you'll need to often destroy these habitats, and that will have a visible environmental impact. Now, you may need to consider other things with energy resources, because these weren't the only reasons perhaps you need to consider. For example, politics, social issues, ethical issues, and economical issues. For example, we have Russia right now with its oil. Social and ethical issues could be people who lose their jobs who work in the fossil fuel industry. Where do they go? Are their jobs not important just because we want to cut down on emissions? Now, our next topic for tonight will be electricity. Now, first of all, electricity is caused by the flow of electrons. Now, by conventional current, we need to say that's from positive to negative. However, if we look at the actual electrons, they flow from negative to positive. I'll be talking in conventional current, so we'll normally talk in this way. Now, if you've got a large number of electrons in, let's say, a wire, and they start flowing, these number of electrons will form a charge, and these are measured in coulombs. For example, a coulomb of charge will have a very large number of electrons. You don't need to know that number for the exam. Now, current is actually how much charge or how many electrons will pass a point in a second. So this is how fast the electrons will flow in a wire. And this is measured in amperes or amps, and that's represented with a capital I, while charge is represented with a capital Q. So therefore, an amp of current is one charge flowing through a point in the circuit in 1 second. And the current as well can be measured with a device called an ammeter. Now, we're going to talk about resistance here. So I'm going to draw a copper wire. These are going to be the actual atoms in it. This is going to be quite a thin wire. Now, if you know your atomic structure, you'll know that there are loads of nuclei or nucleuses in each atom, like from the loads of atoms that form the wire. And you've got electrons trying to pass through these nuclei. Now, if you remember, the nuclei are positively charged, while the electrons are negatively charged. Now, you'll know that positive and negative charges will attract because they're opposite. And what do you think happens if you try and force the electrons through the wire? Now, if you force them through the wire, they have to move through the atoms or around them. So that will be near the positively charged nuclei, and since they're attracted, an electron passing by a nucleus will cause it to move a bit. But with many electrons moving, the several movements cause the atoms to vibrate. This should sound familiar because these vibrations do things. They'll heat up the metal, the copper wire in this case. It'll also make it harder for electrons to pass through. Think about a corridor where there's loads of people and you have to get through them or push through them. It is almost as if the wire resists the current. Now, as you saw on the slide, what the wire will resist the flow of the current. So we need to force the electrons through the wire with lots of energy. This is the voltage. So this is how much energy we need to push each coulomb of charge through a wire. And we can measure this using a voltmeter. And think about, let's say, a narrow water pump. You'll need to use energy or do some work to move the air or water through, let's say, a pipe. And this links with resistance well. So if a component is or wire is more resistive, we need more energy to force the same current through. So therefore, we get the iconic formula V equals IR. So the voltage needed to pass some current through a resistive wire. And we need to label the equation with the correct units. So V is the voltage, which is in volts. I is current, which is in amps. And then the R is resistance, which is measured in ohms. So for example, a 9-volt battery is connected to a circuit with a 300 ohm resistor. So to calculate the current passing through it, we'll need to rearrange the formula. If you like your formula triangles, you'd have V at the top, I, and then R on the bottom. We'll cover up the I, so the current is equal to the voltage divided by the resistance. That's going to be 9 divided by 300, which is 0.03 amps. Another thing you could practice here is, let's say we've got a simple circuit, and that needs 30 milliamps of current, and that's going to be supplied by 12-volt power supply. And we need to calculate the resistance of the whole circuit. Another way you could solve equations like these, perhaps, is write down your equation and then substitute the values that you have in. So we've got 12 volts is equal to the current. So this is in milliamps. We want this in amps. So a milliamp is written as this, MA, so it's a milliamp. Just like millimeters, there's 1,000 milliamps in 1 amp. So this would be 0.03 amps. Now we divide both sides by 0.03 to get the resistance on its own. And that would leave you with 400. And remember the units will be ohms for resistance. Now, you'll need to know about thermistors and uses. So these are going to be special types of resistors. So their resistance depends on their temperatures. So the resistance will decrease as the temperature increases. And the icon for this will be a normal resistor. So this will be like your regular resistor. So that's a rectangle with 2 wires drawn at the side. This time we'll have a line parallel which kind of just cuts across like this. That's a thermistor. And if I draw the graph for the resistance against the temperature, now the resistance decreases as the temperature increases, so the graph would look like this. One application you could use could be cooling fans in computers. So, explain why the cooling fan, represented by a motor, will spin faster at higher temperatures. Now, at high temperatures, this will have a lower resistance. And with a lower resistance and the same voltage, this would mean there's more current. That more current will flow through the whole circuit, including the motor. So therefore, there's more power. Now, another special type of resistor you need to know are LDRs. So these are called light-dependent resistors. So their resistance will depend on the light intensity around it. So their resistance will decrease as the light intensity increases. Now the icon for this would be a normal resistor. And this time it will have a circle around it, and you'll have two arrows drawn in like this. Now, I've got another circuit, and the application for LDRs could be automatic lights. So, with the circuit below, try and explain why the lamp will switch on when it's dark. So when it's dark, this will have more resistance. And what this does is that since the voltage is the same parallel, what will happen is that overall, if you let's say had another resistor actually, it just joins up here. If you ignore this bit here, what happens is the resistance, as the resistance increases, it will take a larger share of the voltage than the fixed resistor that's in series. So when it takes a larger share of the voltage, this voltage increases, this voltage will increase because it's in parallel. So bulb also has more voltage in parallel. And next, another required practical this time for combined science is IV characteristics. So this is where you investigate how the current changes with the voltage across a component. So in other words, how does the resistance change? So you need to be familiar with three components: a fixed resistor, a filament bulb, and a diode. The setup for these components is almost the same, except the diodes will have an extra component to make it safe. And remember to place your voltmeters and ammeters in the correct places. So first you'll have your power supply. Then you will always have a variable resistor. So this is a resistor with an arrow drawn across it like this. Then you'll connect this to eventually your component. Let's say, use a filament bulb, which is a circle with an X like this. And this all connects back to the power supply. What you'll then have, you'll add your voltmeter in parallel. Because in parallel it'll be the same voltage, and then you have an ammeter in series. And just with a diode, what you'll need to do is you'll also need to add an extra high resistance resistor. So for example, for a diode, it'll be the same: your power supply, your variable resistor. This is so you can change the voltage and current. This time you have a diode. You'll have a voltmeter in parallel here again. What you'll need to do is also just add an extra resistor. What this does, it will reduce the current even further because diodes can't really handle high currents, otherwise they'll blow up. Now, the method itself for this practical is as follows. If you remember, you'll first set the variable resistor to its highest resistance, so you'll get a low current and potential difference. Then you'll switch on the circuit, briefly close the switch, so you take readings of the current and voltage. Then you repeat steps 1 and 2 with the variable resistor at 4 more lower resistances, so you slide it down slightly in regular increments or distances. And then you'll repeat steps 1 to 3, but with the wires flipped around at the power supply, so you reverse the current. And then you plot the results from your table and draw a line of best fit. Now, some of these steps I've highlighted because, for example, you need to briefly close a switch so that the circuit doesn't get hot. Now, you don't want the circuit to get hot, firstly for safety. For example, you don't want too much current going through a wire. It can glow red and get very hot. But also, if your circuit gets hot, its resistance, for example, with the component will change. For example, with the lamp, it will increase in resistance at high temperatures. Even with just any old wire, its resistance will increase and you'll get inaccurate readings. And you'll need to repeat these two steps here when you change the resistance, so you get different pairs of readings that ultimately form a graph. And remember, you need to also flip the wires to get the reverse current to get a complete set of data, so that you also continue to form a table and a graph. And ideally, what you get from your results is, for example, for a fixed resistor at a constant temperature or any ohmic conductor, you'll plot your current on the y-axis and your voltage on the x-axis, and you'll see often a very straight line passing through 0, 0. And what you can say about this is that it's directly proportional. So that means as you, for example, double the voltage, the current will also double. So the resistance won't change much. Whereas, let's say for a filament bulb, if I draw the graph, what you should get is almost an S shape, like this. It'll still pass through 0, 0. And what happens is that the filament bulb will actually get hotter. So at this point, the filament bulb will get hotter. And this increases the resistance, so that means you'll need more voltage or more energy to increase the current. And lastly, for the diodes, its IV characteristic looks like this. If you remember with diodes, they basically block current in one direction, and they let current through in the other direction. So you'll get a graph looking like this. So no current passes in the negative direction because it has a high resistance. Next is electrical energy and power. This is for combined higher tier and triple higher tier. So as a recap, voltage is the amount of energy needed to push electrical charge through a wire. So therefore, energy equals the charge times the voltage. Also, since you know that power is equal to the energy divided by time, so how much energy is transferred or used up in a period of time, and you use that formula here, what you'll eventually get is that since the current is the number of charges passing through a point in the second, so charge divided by time, we can replace this here with just I. So actually this is why we get power equals voltage times current. So this is a bit of a maths. Furthermore, what you could do is substitute the V equals IR equation. So if you see V in the formula, you can replace it with IR. And what you get is power equals current, so IR times the resistance times the current again. So you got two I's, so that's I squared times the resistance. So that's an alternative formula if you just have the current and the resistance. And remember that all these formulas will be given to you in the exam anyway. Now time for some calculation practice again. So let's say in electric case will draw 6,000 watts from a 120 volt supply. Calculate the current it needs. So the power equals the voltage times the current. So if you use like your formula triangles again, you'll have this single thing on the top, which is P, and then V and I on the bottom. And you need to calculate the current. So the current, which is I, is equal to the power divided by the voltage supply. So 6,000 divided by 120. This gets us, I think, 50 amps. Next, a UK plug breaks due to a broken fuse when it draws in more than 3,150 watts of power. Calculate and suggest the fuse's rating. Give units in your answer. Now you should know that a UK power supply or voltage is about 230 to 240 volts. So if you use any of these numbers in between, so let's say I'll use 240, because we're calculating the current, this gives you the fuse rating. What you get is 13.125 amps. If you know from class possibly, the only fuses that are sold in the UK or produced are 3 amps, 5 amps, and 13 amps. So it's likely that there was a 13 amp fuse in this plug, so it broke when it had more than the current or voltage that it was designed to have. The last question will be, let's say we've got a 10 ohm resistor, has a maximum power of 0.5 watts, so we can safely have 0.5 watts of power running through it. What's the maximum safe voltage you can have in this resistor? Now this time we'll have to make our own formula, so we know that power is equal to the voltage times the current, but we don't know the current, so if we use V equals IR again, and we rearrange it to get current, we have current equals voltage divided by resistance. And if we put this, so whenever we see I in the equation, we write V divided by R, we get a new equation, which is voltage times voltage divided by resistance. So you get V squared divided by R. So that's a new equation I've just formed right now. So we know the resistor has a maximum power rating of 0.5 watts. So that's our power. That's equal to our voltage squared, we don't know yet, divided by its resistance, which is 10. So if we rearrange this, you get 0.5 times 10 is V squared. Therefore, the safe voltage it can handle is about 2.24 volts. So basically, if you put more than this much potential difference or voltage through the resistor, it's likely going to heat up and basically burn or blow up. Now, the same group I mentioned, which was combined in triple higher, needs to know about the national grid. So the national grid is a network of wires that will connect homes to like electrical producers. So these can be from, let's say, nuclear power stations, they can be just coal power plants, and so on. So you'll need to know how actually the national grid efficiently transfers electricity from the sources to the homes or users. Now I'm going to have this diagram right here. So let's say we have a source, let's say a coal power plant, and what happens to the power is that it goes through a step transformer. Now you don't need to know exactly how it works or do any calculations with them. Is what you need to know with a step-up transformer, it increases the voltage and decreases the current. And this is good because when we transport it over long lines, let's say from a power plant in London all the way up here to the northwest, you'll want a low current because low currents will not increase the temperature of the wire as much, and therefore less energy is lost to the surroundings. So that's why it's more efficient. So lower current, less heat, less energy lost. And once you get to the actual town or village that you want to supply power to, what you don't want is very high voltage. We're talking about thousands of volts. You don't want that going through the power supplies at home. It's too dangerous. So use a step-down transformer, which does the opposite. It will decrease the voltage and increase the current. So it's safer for our homes, and we can kind of afford to put like a higher current through these shorter power lines because it won't travel that far. And then it eventually gets to you, where you can use electricity for what you like. I won't ask. Next are electric fields. So this is actually for triple foundation. So these people may be asked to draw the electric field lines between two objects that have charges. So the lines go from positive to negative charges. Like charges repel, while opposite ones will attract, and that the strength of the electric field is stronger when you get closer to a source. And actually, this is similar to magnetic fields. In fact, electrically charged objects will then interact in magnetic fields. For example, if I have two equally positively charged spheres spaced at a distance and held together, I could draw them eventually like this. So they'll repel each other and exert a force in each other pushing away because the charges are like and equal. There are two ways you can increase this force to make the repelling force stronger. So you can decrease the distance, or you can make the charges stronger. Now that's going to link to static electricity. So let's say we have two things, let's say a cloth and a plastic rod, and we rub the two together. Electrons are transferred from the cloth to the plastic rod. Why are the two now charged? And in what way? So if we lose electrons, this is a link to chemistry. So we lose something negative, it becomes a positive charge. While the opposite is true. If we gain electrons, we gain a negative charge. So if we add something negative, it gets lower. So we get a negative charge if we gain electrons. So therefore, the cloth becomes positive, while the rod becomes negative. Now let's say the plastic rod hovers above some loose pieces of tissue, and then we pick them up. Now explain why this happens, even though the tissue isn't charged at all. So let's say we've got a bit of tissue here, and we've got, let's say, the rod that's going to pick it up. And that's going to be a negative charge. Now what happens is electrons are negative and they get repelled. So that will get pushed over to the sides here. What we've done is we've got a slightly positive charge because when we push electrons away, when there are fewer electrons, we essentially almost lose them. So we have a positive charge on this top side and then a negative charge on the bottom. So what we've done is we've induced an electrical charge. And now that since these two charges are opposite, they get attracted, and that's why the tissue can be picked up with an electrically charged rod. Now let's say the plastic rod, which is negative, is placed near a negatively charged plastic ping pong on the table. What happens? So what happens is, for example, since they're negative, We've got the rod here, we've got the ball here. They get repelled. So the ping pong ball is like pushed away, almost at a distance. Now, lastly, for static electricity, this is still triple foundation. You'll need to know a few applications. For example, spray paints. So the spray paint is charged when it's sprayed out of a hose before landing on an oppositely charged workpiece, let's say a car. Now, it'll be an even coat of paint because when you have the hose here and you have the paint going out, all of it will have, let's say, a charge like something positive, and that will all repel. This will all go outwards, and that gives an even coat. And lastly, the paint will stick much better effectively because the paint layer is positive, while the car's metal is often negative. And these two will have opposite charges and they'll stick together much more. And it'll be harder to, let's say, scratch it off. Now we're on to a new unit, which is particles, and that's for all groups and tiers. So when we're talking about the properties of particles of each state of matter, what do we mean by the arrangement, movement, and energy? So the arrangement is how well they're arranged. For example, how will you draw them? For example, solids will be in regular rows. Movement is how they move. In terms of, let's say, speed, well, that's even if they can move. And then energy is just how much kinetic energy, for example, the particles have. But we'll get to that in a bit. Now, we'll apply each of these to the state of matter. So I'll draw a little table here. Solids, liquids, and gases. So solids will have particles arranged in regular rows, tightly packed. So basically there's no space in between each of these particles. That makes solids kind of hard to compress. Liquids are still tightly packed, but this time they have an irregular arrangement, so they aren't arranged in rows, just like solids. Whereas gases, they're also irregular, but particles are far apart. Now, in terms of their movement, solids, like particles, can't move, but they can vibrate. Liquids, they can move, just slipping past each other. Or rather past other molecules. And lastly, with gases, they can move quickly and freely. This is due to them being far apart and they won't have, let's say, strong bonds or forces that try and bring them closer together. Now, with energy, I'll put them in a little scale. So 1 is the lowest, and 3 is the highest. So solids will have the least amount of energy because they can't move much. Liquids will have more energy than solids, but less than a gas. And lastly, gases will have the highest energy. Now, you may have some limitations. This is a common exam question. So limitations would be, well, what does the particle model of matter not show? You'd often show these as, let's say, spheres. One of them could assume, perhaps, well, particles aren't solid spheres. We've known that for decades because of the Alpha's gassing experiment. They're literally mostly empty space. Many of these diagrams won't show movement. Some other limitations could be they're not 3D, and so on. Next is density. So these are still all groups and tiers. So what's meant by density? So density is how packed something is, so how much mass there is per unit of volume. So density, as a formula, is equal to its mass divided by the volume. And if we use the standard international or SI units, we usually measure mass in kilograms and volume in cubic meters. So when we divide the mass divided by the volume, we get the units for density being the unit for mass, which is in kilograms, divided by its volume, cubic meters, or M3. Usually you could get, however, some other different units. For example, you could get its mass in grams and then its volume in cubic centimeters. So the density for like units would be unit for mass. Then you'll have a slash, then the unit for volume. And usually you have to pay attention for the units that the answer like wants. For example, you may be asked to give your density in kilograms per cubic meter or grams per cubic centimeter and so on. Now we can apply density in a few of ways. Let's say we've got a liquid with a known density. So what can you say about the density of objects that float or sink? So objects that float will have a lower density, while objects that sink will have a higher density. Now, this is a new question that I've made recently. So if you know, not known already, let's say with drinks, ice floats on water. So given what you know about, let's say, solids, liquids and gases, like their particles, why would you not expect ice to have this property? Because remember, ice and water are the same thing. In other words, explain why you would not expect solids to be less dense than liquids. Four marks. And I'd sum it up this way. First of all, solids are packed closer together. And you'd usually have to mention particles in these kinds of questions. This is because they have strong intermolecular forces. They also have the lowest energy and can't move. So that means you'd expect particles to be close together, and that means they have the highest density. Whereas liquids, they can sort of like slip past each other, and you'd have them to be like have a bit more space, if you like. Now, for triple science, they'll have a required practical for finding an object's density. So if you remember, the formula for density is mass divided by the volume. You only need to find the mass and the volume of an object to find its density. Simple as that. And then what you can do, the practical is based around finding each of them. The mass is quite easy. You'd use a top-pan balance. But for the volume, it's a bit different, or a bit harder. For a regular solid, it is quite easy. You'd often measure any dimensions and do a bit of maths to calculate the volume. For example, if it's a cube, you'll measure its side length and then cube it. However, if you've got, let's say, an irregular solid, let's say a lumped piece of, a rock or clay, you'll need to use an eureka can. So that's one of these little cylinders in the spout at the side. What you'd first do is fill it up until it just reaches the spout. Insert your objects, and then you'll collect any displaced water. Because when you insert the objects and it sinks down, the water will rise slightly to make space for the object. That's the displaced water that will fall out the can, and that gives you the volume of the object. The last thing you could be asked to measure the volume on could be a liquid. And put simply, just use a measuring cylinder. And it's helpful that measuring cylinders are already in cubic centimeters, for example. And that's it really, to calculate an object's density. Now, triple science also need to know about internal energy. So from a recap from Unit 1 is, for example, describe the energy transfer when a Bunsen burner heats a sealed container of water. So the Bunsen burner is thermal energy or chemical from the gas. That will decrease. And then the thermal energy of the water will increase. So it'll get hotter, usually. Now, usually you'd sketch the temperature inside the container along with time. What would happen is, initially, since it's a liquid, its temperature will increase. But then it won't for a bit. We'll have a flat line, and then it will increase again. So label these 1, 2, and 3. So at the first point, we've got the water increasing temperature. And secondly, we've got the water staying at temperatures, but this time is actually boiling, so turning into a gas. Which would be water vapor. Then lastly, the water vapor heats up or increases in temperature. Now, why does this happen? So as said in the previous slide, the thermal energy store of the water increases. However, different things happen when heating. Two things can happen. So it's either a change of state, as I said, or increasing in temperature. And this is due to how particles move. So first, you may be familiar with kinetic energy. You know kinetic energy as movement. Now, how fast particles move is actually linked to temperature. The definition of temperature is the average kinetic energy of some particles. And lastly, the other part of internal energy is potential energy. So this is how particles interact, or the spacing, or the distance between them. They've got more potential energy if they're spaced further apart. And that's linked with states. Because remember, at different distances, you'll have different intermolecular forces of attraction, and that means they can move differently. Next is specific heat capacity. Well, this is really just instead a, well, practice calculation. So define specific heat capacity. So this is the amount of energy needed to heat 1 kilogram of a substance by 1 degree Celsius. Now, here's the practice calculation. So let's say we've got a flask containing hot milk, and that cools from 60 to 45 degrees, and that releases 23,520 joules of energy. And the specific heat capacity of milk is 3,920 joules per kilogram degree Celsius. So calculate how much milk was in the flask. Again, we could somehow use formula triangles for this, even though we got loads of variables. So this E would go on top, since it's on its own, and everything else is multiplied. I did write everything else on the bottom. M times C times that triangled circle thing, or delta theta. We want to find the mass. So if we cover this up, so the mass is equal to the change in energy divided by C times the change in temperature. Then we'll substitute the numbers in. So the energy released is, or the change in energy is 23,520. That gets divided by C, which is this number here, the special number, 3,920, the specific heat capacity, times the change in temperature. So that decreases by 16 minus 45, which is 15 degrees Celsius. Put this into your calculator. And you get 0.4. And remember that mass is usually measured in kilograms. That's it, 0.4 kilograms of milk. So all this specific capacity is to do with the change in temperature, and this is to do with the kinetic energy store. Now, for the other energy store, the potential one, this is measured with specific latent heat. So this is the amount of energy needed to change 1 kilogram of a substance from one state to another. Now, they'll have special names such as fusion, which is solid to liquid or back from liquid to solid, and vaporization, which is from liquid to gas or gas to liquid. And you'd see it written as like LF for fusion and LV for vaporization. And this is your simple formula. energy is measured in joules, mass is measured in kilograms, and the specific latent heat is joules per kilogram. Because remember, that's the amount of energy needed to change 1 kilogram of a substance. So, number of joules or amount of energy needed per kilogram to change something from one state to another. Now, here's another harder question. So, what happens is that the specific heat capacity question can be combined with other stuff that can be combined with other formulas. So let's say we've got an aluminium kettle with a power rating of 250 watts, and that heats up a very small amount of water, so 250 milliliters. And there's a bit of information: 1 milliliter of water is 1 gram of water. Now, the water temperature before the kettle was switched on was 20 degrees Celsius. Calculate the final temperature of the water when it was heated for 1 minute and 40 seconds. And you may use the formula this. So delta equals mc delta and theta. And you can say that C, or the specific heat capacity of water, is 4,200 joules per kilogram degrees Celsius. And the final formula I'm also going to give you is power times time equals energy. And this gives one big clue. Try and pause the video and work it out for yourself. So first we have to figure out how much energy is transferred. So we know the power rating of the kettle, and we know how long it was switched on for. So this means we know that the energy transferred to the water, like with heat, is equal to its power times the time. So the power is 250 watts times the time in seconds. So there's a minute and 40 seconds. So there's 60 seconds in a minute. So there's 100 seconds in total. This gets us 25,000 joules of energy. Now, we want to find the temperature of the water, the final temperature. We partly can do that by figuring out the change in temperature. So if we draw the big formula triangle out again at the top, we want to find out the change in temperature. So we'll just highlight this out. We could ignore, we can just see everything else. So the change in temperature is equal to the energy divided by the mass times the specific heat capacity. So if we substitute our numbers in, so we know the energy now, 25,000 joules. We divide this by the specific heat capacity, which is actually the mass, which is 250 milliliters. So 250 milliliters, that would be 250 grams. And we want this in kilograms. So that's 0.25 kilograms. So 0.25 the mass times the specific heat capacity, which is 4,200. Put this into a calculator. And we get a decimal answer, but it's about 23.8 degrees Celsius. So this shows the temperature increase. So we know it started at 20 degrees Celsius. So the final answer is you add this on to 20 So the final temperature is 43.8 degrees Celsius. Seems like a lot of work for just 4 marks. I hope you got this as your final answer. And if you did, well done, because it's a hard question. Next is for combined science higher tier. So describe the movement of gas particles. So gas particles, as you know, move around freely in random directions in straight lines. They're all just far apart from each other. Now, a gas is kept in a sealed container. Now, what's meant by its gas pressure? So if we got a sealed container here, its gas pressure will be from the particles, which are very small, moving in random directions. Eventually, a gas particle is going to hit the edge of the container and basically bounce off it. This exerts a little force on the outside. And this force is what causes the pressure. And we can change the gas pressure in a variety of ways. You'll need to know about 2 factors, one of which you need to explain, and you can assume that the other factors are kept the same as well. So let's say one factor is the volume of the gas container. So if we shrink the gas container, what happens is, since we've got, well, a smaller container, the same number of gas particles will collide more frequently with the walls, and that means there's more force exerted and higher pressure. But you don't need to explain that. What you do need to explain is the temperature of the gas, how it affects the gas pressure. Now, as you know, temperature, this is the average kinetic energy of particles. So kinetic energy also links into movement. It's like how fast something travels. So if something travels more quickly, like all the particles will travel more quickly, they are going to collide with the walls of the container much more frequently. So higher temperature will have a higher average kinetic energy, more movement, that means more frequent collisions, again with the edge of the container, which exerts a larger force, increasing the gas pressure. So that means a higher gas pressure. So overall, increasing the temperature will increase the gas pressure. Now the final topic for tonight are atoms. So this is going to be a crossover with chemistry. So firstly, I'd like you to draw a diagram of the current nuclear model of the atom. So what we know is already that we have the nucleus made up of protons, and let's say some neutrons as well, which I'll draw blank. So I'm going to draw, let's say, the solid dots as protons, the open dots as neutrons, and then I'll have some green dots, which are electrons. And if you know from chemistry, you know that these electrons will orbit the nucleus in shells, or energy levels. And you also need to know the mass and charge of each subatomic particle. So if I draw a little mini table here again, the mass and charges are only just numbers. So we've got the mass in this column, and the charge in the second column. So protons have a mass of 1, neutrons have a mass of 1, and electrons have a relative mass of 0, or you can just say very small. Whereas charges, protons will have a charge of positive 1 or 1 plus, neutrons will have no charge overall, and electrons will have a 1 minus charge. Now, like chemistry, you'll need to know about isotopes. So the most common isotope of chlorine, for example, is chlorine 35. So this is shown in the periodic table, as shown like this. So you'll have Cl, and on the bottom you'll have 17, that's the number of protons and electrons, and 35 on top. So this is the mass number. This is the atomic number. So the mass number is made up of the number of protons plus neutrons. So that's because the protons and neutrons have a mass of 1 each, and the atomic number is based off the charge, so that's equal to the number of protons, and it happens to be the number of electrons as well, because overall an atom has an overall charge of 0 or neutral. So in this case, find the number of each subatomic structure in the isotope. So we can already see from the atomic number there are 17 protons, because the atomic number tells us the number of protons. Since the overall charge of an atom is 0, and since protons and electrons have equally opposing charges, proton is a positive one, electrons are negative ones, there must also be 17 electrons. Lastly, based off the mass number, 17 protons and some number of neutrons make up a mass number of 35. So we just do 35 minus 17. This gets us 18 neutrons. And we've already defined atomic number and mass number. And therefore we can use these terms to explain what's meant by an isotope. So an isotope is the same element, so same number of protons, but with a different mass number. As in, it'll have a different number of neutrons. Now, this is also another crossover with chemistry, and this is the model of the atom. This could be, let's say, a high mark question. You could be asked on how the atom model was developed. So, like other models, the atomic model has changed over time. This is because experiments were done, and the evidence from these experiments either supported or had evidence against these old models. So we changed the model so it supports the new evidence. So first, the Greeks thought the substances were made up of atoms. So these were very solid, small spheres that couldn't be divided up further. That was the case until the 1900s, until this guy called J.J. Thomson discovered the electron. He was playing around with charged stuff, which you don't need to know about. So at that time, they knew the atom's overall charge was neutral, but they didn't know about the nucleus. So that's where we made the plum pudding model. So it explained the overall neutral charge. So we had an overall sphere of positive charge, and we had negatively charged electrons embedded to it. So rather stuck onto it. A bit like this. Some would be inside, some would be outside. That was the model of the atom until not long after, until some of J.J. Thomson's students did their own experiments, the alpha scattering experiment. So the three guys, Rutherford, Geiger, and Marsden, carried out the alpha scattering experiment in 9 years later, in 1909. So they fired alpha particles, which were positively charged. If you're wondering, it's a positively charge of 2 plus. And these were fired at a thin sheet of gold. What they found was, as a result, that the atom is mostly empty, has a concentrated or very small positive charge, or a very small area of positive charge, and they've also got a concentrated mass. So this is why we have the nucleus, or the nuclear model of the atom. If you're wondering, the experiment was like this. So as expected, they expected the alpha particles to just deflect slightly. But three things happened. First one was, most of the alpha particles simply passed through, with no deflection at all. This meant the atom was mostly empty. And the two other things that happened, some alpha particles were deflected more than expected, and some alpha particles were even sent straight back. This meant there was a concentrated positive charge. This meant there was something in the center very concentrated or very strong with a positive charge that made those alpha particles, which were also positively charged, like repel away and get pushed away, either sent back or more than expected. This meant that all the mass had to be concentrated in the nucleus. Now, this model wasn't the end, because afterwards Niels Bohr found that electrons weren't just random, they were organized in shells. He did some calculations which you don't need to know about in depth. And lastly, James Chadwick found the existence of neutrons. So these had the same mass as protons, but with no charge. This explained the existence of isotopes. So this is where you have the same element, but with different masses, or different numbers of neutrons, if you remember. Now, moving on from atomic structure is all of combined science, like content, which is nuclear radiation, which is this topic. Now, the problem is, some atoms have an unstable nuclei, so they don't stay the same due to some forces within the nucleus. As in, they can't keep the nucleus together, it's not strong enough on its own. As a result, the nucleus will release radiation of all sorts to make it stable, to make it smaller so it can hold itself together, if you like. This is called nuclear decay. Now, it's important that nuclear decay is a random process. We don't know actually when, let's say, some radiation is going to be emitted. It's random. And you can measure its activity, like how many particles or bits of radiation you detect in becquerels, or the number of decays as a count, or like counts per minute or counts per second. Now, there's a few properties of each type of nuclear radiation, such as its structure, mass, charge, ionizing strength, range, and what materials stop it. And that's demonstrated on this table here, which I'd suggest you should screenshot. Now, alpha particles are a helium nucleus. This means they have 2 protons plus 2 neutrons. That means they have a mass of 4, relative mass of 4. They have a charge of 2 plus, because there were protons, each with a 1 plus charge, and ionizing strength is quite high. Ionizing just links to the charge. So this would do lots of ionizing damage to, let's say, your skin. You wouldn't want to touch something that emits alpha radiation. This was because these alpha particles will then destroy your DNA and cause mutations, which cause cancer, which cause you to die. I wouldn't say cause though, because it would rather contribute or be a risk factor. Anyways, we could also talk about the range. So alpha particles don't travel more than, let's say, 10 centimeters, and they can be stopped by a sheet of paper. So really, at a distance, you're actually safe from alpha particles. Now, beta particles are just high-speed electrons which are emitted from the nucleus. Its mass is 0 or very small. If you remember from the atomic structure, its charge will be opposite, so 1 minus. Electrons are negatively charged. Its ionizing strength is, well, let's say, medium, as in less than the alpha particles. Its range is a bit further, I'd say about a meter or so, and it can be stopped by a sheet of aluminium. Gamma particles are just electromagnetic waves. These will have no mass and no charge, so practically their ionizing strength is basically there isn't any. Its range is practically, however, unlimited, because we can see examples of gamma rays in the universe in background radiation, and gamma rays can only be stopped by a thick layer of lead. Now we're on to the last 3 slides. Now we have nuclear decay equations. So when an atom decays, it can become a new element, because with alpha particles, you lose 2 protons and 2 neutrons. So the number of protons change. Whereas with a beta particle, you lose an electron, and then a proton or neutron becomes a proton. And we can represent these new elements and the radiation in decay equations. And remember that the mass remains constant on both sides, as well as the total charge. So if you remember, on the top you have the mass, and then the charge on the bottom. That is really the atomic number. An example could be radium decaying by alpha emission to form radon. Now radium has a symbol Ra. We'll say 226 here. I'll have to quickly get a periodic table. Leave that alone. Please leave that alone. So radium has an atomic number of 88. Put that away. Leave my wallet alone, James. So when it decays, we'll draw this with an arrow. We'll write the new element, which will be radon. You'll be given the symbols, and you'll usually be asked to fill in a missing box here, which is going to be the alpha particle. You can usually write it as an alpha like this, a bit like an A, and then you'd write it as if it's an element. So it has a mass of 4 from the 2 protons and 2 neutrons, and it has a charge of positive 2 from the 2 protons. So what happens is you subtract 4 off the mass number, and then subtract 2 off the atomic number to get you new elements. So that's alpha decay. So decay can be called emission. So those are two similar things. Another example could be tritium, which is hydrogen, decaying by beta emission to form helium. So tritium is hydrogen with a mass of 3, an atomic number 1. Now, this forms helium and the beta particle. So the beta particle is a high-speed electron. Electrons don't have a mass, so the mass stays the same with beta emission. Electrons also have a charge of -1, which we'll write as its atomic number. So what we do is we actually add 1 to the atomic number. And lastly, we've got cobalt-60 decaying by gamma emission. Now, nothing actually happens with the element because gamma rays have no mass and no charge. And that's it for the decay equations. The penultimate slide for tonight is half-life. So remember that radioactive decay is random, and that a sample of radioactive material will have its activity. So if you're contaminated with something that's radioactive, the thing that's been contaminated, let's say I, for example, touch a radioactive source, my hands can become radioactive because the actual substance has gotten to my hands and now, yeah, it's radioactive. Whereas irradiation is where I could be exposed to radiation, but I never touch the source itself. I've been exposed, but I'm not contaminated, so I'm not radioactive myself. And lastly, these two exposures. So usually when you handle the transport samples, you would keep the radioactive samples in lead-lined boxes. This is because lead will absorb all the radiation, if not most at least. So you don't get exposed to it. And lastly is contamination. You don't want to touch the radioactive samples yourself, so usually you'd use tongs. Use long tongs. So this basically avoids like is direct skin contact with a radioactive sample. And usually in this example, you'd get a mark for your method. Like, so you measure to reduce, let's say, irradiation or contamination, and then another mark for your explaining why that reduces irradiation or contamination. So just remember the definitions, and then I think you'll be okay for this. So overall, that's it for physics paper 1. Even though it's after half term, I hope you still have good luck with this and return to it soon. Just let's say before the night before exams. So overall, that's it.